Good morning, everyone. Today I will give a lecture of an advanced topic titled as When AI Meets Spatial-Temporal Data. Well, I think nowadays everything comes with AI tends to be a super hot topic, um, drawing so much attention not only in the industry but also in the academic area. A few weeks ago, you have got a course talking about the spatial temporal data. So now I'm trying to provide a view to you what is going on with spatial temporal data using AI techniques. So hopefully you can really grab something from this lecture. Before going to the topic, please allow me to introduce myself a little bit. As you know, I am the guest lecturer of this course, and my name is Dan, or you can also call me Doris. Um, I'm now doing the postdoc in transport engineering group at the civil engineering. I got my PhD degree from ITEE at the data science group. My research focus during my PhD was on the spatial temporal data analytics, supervised by Xiaofang Zhou and Sibo Wang. Professor Xiaofang is the leader in our data science group at UQ. Sibo was the postdoc at UQ, but now he is a professor at CUHK at Hong Kong. If you'd like to know further about me, and here's my personal website, welcome to drop a visit. Okay, let's go to today's topic. When AI meets spatial temporal data. So basically, this is about how people apply different types of AI-based techniques to deal with the spatial temporal data and address the problems in the domain of the spatial temporal applications. So when we look at the spatial temporal side, there are many different types of applications, such as the POI localization, ride hailing, routing, traffic prediction, and so on and so forth. In terms of the AI techniques, you may have heard about the Bayesian network, Markov network, and support vector machine, and different kinds of the neural networks. Some of you might have the prior knowledge about these kind of techniques, and some of you might not, but it's fine. Don't worry about that, because I'm not going to dig too much in depth about the technical stuff. So basically, you will get a high-level idea and some overall pictures about how these kind of techniques are applied to address the problems in the spatial temporal. Let's have a recap on different categories of spatial temporal applications. Actually, there are so many applications around us that involve the spatial temporal data. For example, the routing service on Google Map, or we can say the navigation service. Usually, when we give the starting and destination locations, the Google Map will return a path for us, maybe the shortest path or the farthest path, and then guide us to the location we want to go. And another example is the taxi hailing service, like Uber. What we need to do is to type your current location and maybe the targeted place as well, and then a few minutes later, the Uber will come to you. The spatial temporal data also exists in the social networks. They can recommend a friend to you based on your current location. And also, some people sometimes post a twist with a geotag, and then we can infer their trajectories based on their twist. And what else? We also have the traffic management. There are a lot of detectors and cameras on the road network, capturing the occurrence and sometimes also the speed of the vehicles running on the road. Um, and most vehicles actually will have their built-in GPS devices that can generate a large volume of the vehicle trajectories. And the availability of such kind of data usually offer valuable information for the transportation department to better manage or sometimes disperse the traffic on the road. In addition, the biologists try to study the uh, migration patterns of the animals from their migration trajectories. So as we can see, uh, the applications using spatial temporal data are actually ubiquitous. What kind of technical supports are necessary for the applications just mentioned? You might have seen this picture a few weeks ago. And indeed, this picture covers most of the techniques and topics in processing the spatial temporal data. Hmm. Considering the applications like the navigation surface, what kind of method will be involved? Mm. When given starting and destination locations, the first thing need to do is to run a query on the road network to find a proper path between the starting and destination location, like the shortest path query. And then during the navigation, what come to the service system are actually the periodically captured and uploaded GPS points from the running vehicle. And then the system will do the map matching to assign the vehicle to the specific road segments such that it can tell you whether you're driving in the right path or where to go next. So this is about navigation. What about the taxi hailing service? When you set up a request on the app like Uber, the system will find the cars close to you by running the KNN query on the road network and then assign one of the available cars as the response coming to you. Well, actually, different kinds of the query processing regarding the spatial temporal data have been studied by our group for many years. And one of my research topics during my PhD was on the KNN query of moving objects for the applications just like the taxi hailing service. And we mainly strive to build some kind of index structures for the moving objects such that we can answer the query very efficiently, even in the case that the locations of the objects are always changing over time. So if you are interested in this topic, we can have some further discussion maybe offline. So we now have got some ideas on the spatial temporal side. What about the AI side? The artificial intelligence. So the artificial intelligence is defined as follow by someone, and not me. It is a branch of computer science by which we can create intelligent machines which can behave like a human, think like humans, and able to make decisions. So it doesn't work as the previous examples that we need to develop a deterministic algorithm to tell the machine what to do step by step. It can learn from the data itself. The artificial intelligence is developing so fast nowadays, and there have been so many applications applying the AI technique in many domains. For example, the AI machine can play strategy games like chess and even can beat a human professional player. I guess what comes to your mind must be the AlphaGo, right? Which is developed by the DeepMind in Google. It's uh, it's really an amazing story. And another example is the self-driving, also known as the autonomous vehicle, which combines sensors and software to control, navigate, and drive the car without human involvement. But most of these self-driving techniques are in their testing stages. Um, we will see hopefully soon when this kind of cars can be used by us in reality. There are so many other cases, such as the Siri on your iPhone, and some robots conducting tasks for human in some very risk situations. And maybe in the future, the one sitting on the other side of you giving the lecture will become an AI machine, and we will see. So, what kind of techniques are there in the AI field? When we talk about AI, many people um, will also come up with machine learning and deep learning, thinking that they're the same thing. But actually, AI is a much broader field, and it includes the machine learning, and deep learning is just a sub area of the machine learning. Concretely, compared with the machine learning, AI is so as I mentioned, broader concept that includes many subfields such as the expert systems, agent system, and also knowledge representation, and so on. And machine learning is actually one kind of the methodologies to achieve the different goals in AI. However, today's lecture is not about an introduction of the artificial intelligence or machine learning. So I will just very briefly mention what kind of techniques are included in the machine learning and in particular in deep learning, since the topics discussed later are mostly about the deep learning methods. In general, the machine learning includes different categories of learning algorithms. It includes the supervised learning, unsupervised learning, and also the reinforcement learning. The supervised learning refers to the learning algorithms that try to learn a mapping from your input variables to an output. And usually we can train the models with the sample data sets so as to get the best mapping where the correct answers of the output variables can be obtained from the dataset. It is usually applied to deal with classification or regression problems. The unsupervised learning usually try to model the underlying structure or distribution of the dataset. And a typical unsupervised learning algorithm is the clustering algorithm. The reinforcement learning is a kind of learning algorithm that is different from the unsupervised learning or the supervised learning. Usually, it aims to make decision for an agent to take action in one environment at consecutive time steps, where there will be rewards generated in each time step or in the final step. And then the overall goal for the learning is to maximize the reward by taking different actions in different time steps. And it's a bit complicated, but this will not be covered in the rest of this lecture. So we will focus on the deep learning algorithms, and in general there are six typical types of deep learning models like the feed-forward neural network, and the autoencoder, and deep brief network, convolutional network, and recurrent neural network, and also the graph neural network. I'm not going to introduce the details at this point. I may go to some details of the deep learning models in the specific topic we discuss later. So now we have got some ideas on both sides independently. So it's time to look into what exactly is in the intersection of the spatial-temporal data and the AI techniques. So firstly, let's just quickly recap what the spatial-temporal data look like. And we use the trajectory as a typical example of the spatial-temporal data. So in particular, the simple form of a trajectory usually contains an ID and a sequence of location and timestamps pairs, and this sequence is ordered by time. In reality, there could be some additional attributes attached on the trajectory, like whether the vehicle is vacant or with passengers in the taxi trajectory, and what kind of travel mode that this trajectory takes, and the purpose of the travel, and so on. So, a more general form of the trajectory actually contains object ID, trajectory ID, and some property of trajectory, and also a sequence of tuple consisting of not only location and timestamp, but also an additional attribute. So then, what kind of information we can learn from the trajectory data, or we say attributes? So generally, the trajectory data contain the spatial, temporal, and sequence information. From the spatial point of view, we can get the route that one trajectory traverses, and can also infer the underlying road map from a large scale of trajectories running on the roads. And in terms of the temporal perspective, we can observe the travel time for a specific journey, or even on individual road segment, as well as the speed profile. As for the sequence information, we can learn the next movement from the sub-trajectories of one complete trajectory, or maybe by looking at some historical traces, we can infer the destination of the trajectory as well. Moreover, some other information such as the travel modes and personal driving preference can also be captured by the trajectory data. Next, we will look into some examples of applications that apply deep learning techniques on spatial temporal data. Typically, I will introduce 4 topics. Actually, for each of them, there are a lot of existing studies addressing the corresponding problem, but I will only introduce one in one specific topic as the representative method. The first topic is learn to generate map from trajectory. So we know that the trajectory data is a type of sequence of time order points, and then a map is usually represented by a graph, which contains a set of nodes and edges connecting 2 nodes. Now, how can these 2 types of data transferable from one to another? There are many different ways to do that. A typical method is to perform clustering on trajectory points, and then pick and then we can pick up some representative points from different clusters and take this as the nodes for the row network graphs. Um, and then what we need to do is to generate the links between nodes. This can be done by looking back to the trajectory data because we can get the chase and also the direction informations from the trajectory data. Like if there exists a certain number of trajectories passing from one node to another, and then we can generate a link. But the performance of this kind of method, as you can imagine, is not good, right? If the representative points are not the exact intersection of the row network, there will be a lot of the shortcut roads generated, which do not exist in real row network. So the DeepMG, so this work is actually newly proposed work in the AAAI 2020 by a group working on smart city for quite a long time. And they have been working on the spatiotemporal data for many years and proposed so many awesome and effective methods for different spatiotemporal applications. So in this work, the DeepMG, Deep Map Generate, they aim to generate a map from a large set of trajectory and of course by deep learning techniques. This model will take trajectory data as input and then generate a map. But how can it be? So we can look at this picture as an example. When given the trajectory sampling points in picture B, probably as a human, we can manually draw some lines to represent the row segments. But the computers cannot make it. What computer can see are just a set of spatiotemporal points. So if we try to line up all the consecutive points in the trajectory, and that will bring something like picture C, but the actual map or the row network is shown in picture A. So how does DeepNG work? Basically, it develops a deep learning model to generate a map from the trajectory data. And as you may know, most of the deep learning models usually have the input and output data in the forms of vectors, matrices, or tensors. So it needs to do something to produce such kinds of data formats from the trajectory data. Here is how it goes. Firstly, it partitions the space into grid cells, say I times j grid cells for the whole row network space. And then for each grid cell, it extracts some features from the trajectory data. So now the trajectory data have been transformed into a tensor format. Because based on the partitioning, we already have a matrix of the grid cell, right? And then on top of that, each cell contains a vector of feature that comes from the trajectory data. And then as a whole, it becomes a tensor. And later, it will feed the features, the feature tensor into a deep learning model to generate some information that can help to generate the final map. And this is the basic idea. Concretely, there are two types of features can be extracted from the trajectory data, say spatial and transition features. For the spatial feature, it calculates the density of trajectory points in each grid cell and also the number of line segments. And here the line segments is just basically the line between two consecutive points in the trajectory, and also the average speed and directions. For the direction, there are in general 8 directions, the north, south, east, and southeast, and so on. It calculates how many line segments for each directions in one grid cell. So in total, there are 11 spatial features forming an 11 by 1 vectors for each grid cell. And in terms of the transition feature, it captures the connectivities between different grid cells by trajectory. In this case, each cell corresponds to a mask matrix. Like if there exists a certain number of trajectory going across one grid to another grid, the position of that grid will be marked as 1. And the transition features is multidimensional and will be later narrowed down into a tensor. So this picture shows the general framework, and we're now here. We're now here. So the spatial and transition features are generated based on the trajectory data. Then these two tensors are concatenated together and are fed into a deep learning model named T2RNet. I'm not going into the details of this model. It's just like the ResNet. It's kind of applying multiple layers of convolutional neural networks with several different connecting ways to generate different intermediate outputs. So the output of this model is a matrix representing the row central line. So, for example, if there exists some row central line in one grid cell, and then this grid cell will be marked as 1. So this is kind of some morphological way to represent a map. So during training, the ground truth from the real map data will be used to tune the parameters of this model. And so this is a supervised learning. And so now we finish the geometry translation and also get a set of row central lines. So now we only have the lines, and then in the topological construction, some heuristic algorithms are introduced to make the connections between two lines or multiple lines, among multiple lines. So here, it will make use of the trajectory data again to refine the map structure, and this process is just similar with the traditional method that doing the map inference. So I'm not going to discuss too much about the map inference. And so the key idea of this work is to transform the trajectories, which is a set of the spatial-temporal points, into some feature tensors that can be fed into the deep learning model and then infer some row network information to generate a map. So if you are interested in the detail of this model, please have a look at the original paper. The second topic is about the destination prediction. The problem definition itself is very straightforward and easy to understand. What we have for the input is a sequence of sub-trajectory from an original trajectory, and what we need from the output is the possible destination from the original trajectory. For example, I give you my travel trace starting from UQ and then pass by to Wong, and I'm now on the coronation drive. So could you tell me where would be my potential destination? Am I going to the city or to South Bank or Sunny Bank or Gold Coast? A very simple way to answer this kind of question is that you can get all my historical trajectories, and then you match the trajectories that contain a subsequence of trajectory traversing from UQ and to Toulon and passing by Coronation Drive. And then from this set of trajectories, you can extract all the destinations, and then you return the destinations with the highest frequency, and also you can return several destinations as an option of the candidate to select. But maybe you don't have enough historical trajectory data from a single person, right? But it's fine. You can try the same way to use all the historical trajectories from your database. But probably the performance is limited. Here, there's one question. Some of you may have questions like, the destination of a trajectory is usually a single GPS point, right? And then how can we predict a single GPS point that specifically, right? I have to point out here, no, we indeed cannot do that. So as I said in the previous example, the destination can be city or South Bank or Sunny Bank. So all this kind of location indicates a region. So we cannot do the prediction with that high resolution to a very specific GPS point. At least so far we cannot make it. So usually we will partition the space into a region-based like grid cells, and for the whole road network. And then we model the input and output data in the grid cell level. For example, there is one trajectory moving like this. And then after partitioning the space into grid cells, we can then present this trajectory into a sequence of grids, like from N5 to N1 and then to N2 and 6. So now the trajectories here is not a sequence of GPS points. Instead, it's now a sequence of grid cells, like starting from N5 and then to N1 to N2, N6 until N14. And then the predicting result here can be represented by a single cell. Like for example, here it can be N13 or N9. So rather than using the simple way as I mentioned before, there is another solution that applies the Bayesian rule to calculate the probability traversing from one grid cell to another based on the historical trajectories. For example, we can calculate how many trajectories traversing from one grid cell to another, and then we use this number to divide the total number of trajectory in the database such that we can get the probability of traversing from one grid cell to another. And after that, we can use the Markov model to calculate the overall probability from the starting point and passing by the given subtrajectory and then to the possible destination. So this algorithm will return the destination with the highest probability. So although the Markov model can make use of the train information from the trajectory, but it actually relies highly on the transition relationship between two consecutive grids, which means it can only make use of some very previous sequential information from the subtrajectory. So this model named Tor applies the deep learning model to address this problem. So specifically, it applies the LSTM model, long short-term memory model. Here I'm gonna explain a little bit about the LSTM model. It's one kind of the recurrent neural networks. The recurrent neural networks, and also called INNs, are widely used to deal with the sequential data, like the voice, to do the voice recognition, and also on the words. One LSTM model usually contains a sequence, a sequence of units, and the input sequence will be processed sequentially one by one by this sequence of units. In each unit, there will be one input from the input sequence, and there will be one hidden state generated by this unit, which will also be the input of the next unit together with the original input. Compared with the general INN model, the LSTM can learn the long-term dependence from the sequential data, and the reason is hidden in the detail of the models, but I'm not going into it now. Let's come back to the destination prediction problem. The trajectory is actually one kind of sequential data, right? So we can use the LSTM model to capture the chase pattern from the prefix of the trajectory to infer the destination. The intuition is very straightforward, but we need to first transform the trajectory data into a format that can be fed into the LSTM model. In TOR, the trajectory at the beginning is a sequence of grid cells. So it did some trajectory embedding to transform each grid cell into a vector representation rather than just use the grid cell ID. So the method of embedding can consider the speed information, number of nodes in the grid cells, and so on. In terms of the model architecture, it used the bidirectional LSTM, which not only considers the sequentials from the starting point of the trajectory to the current destination of the sub trajectory, but also the reverse order. So in this way, this model can also make use of the historical data dependence traversing on the opposite side. So some other techniques are also applied to enhance the performance of the prediction, such as the attention neural network. So eventually, the output of the model will be represented by a vector, where each element in the vector indicates the probability of one grid cell being the destination of the input subtrajectory. The advantages of deep learning model compared with the Markov model is that we don't need to pre-compute the probability based on the trajectories data traversing from one grid cell to another. We just input the data into the model, and then the model will tell us the final probability of a possible destination. So it's completely data-driven model, right? Besides, it can also capture the sequential information from the given subtrajectory with long-term traversal dependence. So this is all about the destination prediction and how Tor deal with this topic. Next topic is about the travel time estimation. Well, this topic has been studied for years, and there are actually many subtopics that consider different input query and the destination, the estimated targets. For example, given an OD pair and a specific starting time, and then we can estimate the time used to go from the original to the destination and set off at a given starting time. We can find this application on Google Map, right? When you type in a destination, and then the Google Map will give you an approximate time from your location to the destination based on the current traffic condition, and as so in this picture. So this is the basic requirement and also the use case of the travel time estimation, but the ways to achieve this are diverse. A very naive way to deal with this problem is to calculate the distance and then divide it by the speed. And the speed can be based on the average speed of the specific user, or also some commonly used speed value. And a slightly improved way is to make use of the historical trajectory data that use an aggregative average travel time between original and destination. So recent years, some studies try to apply the deep learning models to learn the travel time based on the data itself. And there are different focuses. One is to consider the travel time for a specific path, just like what I mentioned before, given OD pair and then and given specific path. And then the other one tries to estimate how much time usually takes to traverse each road segment on the whole road network within a certain time interval. For example, we can try to estimate the travel time on the Coronation Drive during 8 a.m. and 9 a.m. on every weekday. And then this data can be further used to calculate the travel time for any specific path. However, estimating only the average travel time for each road segment usually cannot provide enough information because the travel time can be a bit fluctuate within a certain time interval, because the speed of different vehicles or the traffic on different lanes on the same road network are not the same. So some studies try to estimate the travel time distribution for the road segments on the road network, and also consider a certain time interval. So look at this example here, the distribution. So this distribution of the travel time means that the probability of traversing a specific road segment in 5 minutes is 0.2, and then you can have a chance to use 10 minutes to traverse this segment, and then the probability is 0.3 to travel within 15 minutes. Actually, we can obtain such distribution from the historical trajectories passing by the road network in some given specific time intervals. However, in practice, there is one significant problem. What is that? To obtain the travel time for one road segment or some specific road segments would be not difficult. But to get all the travel time estimation for every road segment on the road network would be not easy. But why do we need the travel time for every road segment? This is because, as I mentioned, the eventual objective is to get the travel time estimation for any arbitrary path on the road network. We usually can easily get a travel time distribution for some road segments where the traffic is very busy. But as you can imagine, not every road segment has the vehicles running on it, especially when given a specific time interval. Usually, only a very small portion of the road segments contain traffic. And this is so-called the data sparsity problem. And in this case, we can only get the travel time distribution for a small part of the road segment. And this picture shows an example. In this small road network, only the path E5 and E6 contain the travel time distribution within a specific time interval. And the work named GCWC actually tries to fill the missing data by a deep learning model, or we can say it aims to estimate the travel time distribution for the road segments that have no traffic within a specific time interval. So the network model looks like this. It combines graph convolutional networks and an autoencoder model to do the estimation. And the input data contains the adjacency matrix of the road network and also the travel time distribution matrix for each road segment. Because each row segment has a vector representing the distribution. So we say that this is a travel time matrix. And these two matrices are formed to be the input of the graph convolutional network. By this graph convolutional network, the spatial and temporal dependence from the neighbors of the row segments can be propagated. And in this way, the travel time information can be inferred from the neighbors of the row segments. And after several layers of the graph convolution, the missing data for some row segments can be filled up. And then later, the consecutive autoencoder model and the fully connected layer are working similar with the usual feed-forward network to capture some other correlations from the dataset. And then you can just imagine this as a black box, and eventually we will get the travel time distribution for every row segment, which is represented by the travel distribution matrix. You may have questions on how to do the training, right? And actually, during training, we will have to use the dataset that every segment contains the travel time information. And we first randomly remove the data, the value from some of the row segments, and then make this as the input of this model. And then the output will be compared with the ground truth, which is actually the one that with the full travel time distribution values. So there are many other types of the travel time estimation solutions that apply other deep learning models, such as the LSTM or the convolutional networks, also say CNNs. And one of my project students is doing a kind of literature review on this topic. So if anyone is interested in this topic, we can have some further discussion personally. And so this is all about the travel time estimation. Okay, so now let's go to the next topic about the traffic prediction. Actually, this topic is somehow a little bit similar with the travel time estimation. This topic is the last topic that I'd like to share with you today. Traffic prediction is actually a very fundamental problem in transport engineering and has been studied by the academy for decades. It plays a very important role in traffic management because if we can know the information, like the traffic flow information happen in the future, and then we can act in advance for the route planning or the traffic control to eventually avoid the congestions on the road. And in general, the objective of one traffic prediction task is to forecast the traffic measurement, like the number of vehicles running on the road, in the next coming time steps, and based on the historical traffic data, or or some other source of data like the weather or time of day and some POI information and so on. A very naive way to do this is to just get the historical average measurement for each road segment. But this is definitely not accurate. And then the most popular way is based on one model named the ARIMA, the auto regression integrated moving average for short. Which is widely used for time series forecasting, and actually the traffic measurement is also one kind of the time series data. But recent years, many deep learning based models are proposed for the traffic prediction, and the overall framework of the models applying the deep learning techniques actually looks like this picture. The input data is usually formed by traffic measurements in the previous several time steps. For example, if we would like to predict the traffic flow on the Coronation Drive at around 9 a.m., and then the input data is actually a sequence of the traffic flow, maybe from 7:30 to 8:30 a.m. That means we only look back a little bit to see how was the traffic flow just occur, because this information is actually highly related to what will happen next. So the raw data of the traffic measurements, such as flow or occupancy or also the speed, are captured by different data collection methods, and most of them are captured by the route detectors installed on the roads, and some of them are based on the vehicle trajectories. This traffic data needs to be pre-processed into vectors or matrices, and then to feed into different deep learning models. And the deep learning models will eventually generate the predicted results also in the format of the vectors or matrices. During model training, these results are compared with the ground truth in order to tune the parameters of the models. And actually, different prediction models have different ways to model their traffic data. For example, some of them focus on one specific road segment. They aim to predict the traffic flow on a specific road segment like a bridge. And some of them will try to handle the citywide road network for traffic prediction, like to predict the traffic for each road segment in the whole Brisbane city. So now let's have a look at one example of the traffic prediction model named the ST ResNet. This model focuses on the region-based traffic flow. It aims to predict the inflow and outflow for the regions. So firstly, it needs to partition the whole road network into grid cells, just similar with some of the previous works. And then the overall objective is to predict the inflow and outflow for each grid cells across the whole road network. And this can provide the mobility patterns and also the tendency of movement for the whole population in some specific time intervals. So like moving from the residential area to the official area in the morning, and then do the opposite in the afternoon. So having this kind of information in advance can help to control the traffic lights or schedule the traffic light cycles to allow some very heavy traffic and then to get more green time for travel. And here is how the model looks like. It used the historical data as input from not only the recent passing time step, but also some periodical historical data at the same time step as the predicted time. For example, if we would like to predict the traffic flow at 9 a.m. and then not only the flow data between 8 to 9 a.m. on this day is used, but also the flow data at exactly 9 a.m. but from previous several days and also from previous several months, but on the same dates, just like Tuesday, are used. And then the historical data are fed into three different ResNet models. The intuition of each ResNet model is that it can capture the spatial and temporal dependence from some nearby regions and then to infer the prediction results. And the output from these three ResNet neural networks are then fused together with the feature matrix generated from other data sources, such as the weather and then time of days, like whether it's weekday or weekend or holiday, and and then get the final prediction result. So this is the basic idea of the ST-ResNet model. And actually, there are some other traffic prediction models that apply different kinds of the deep learning techniques, such as the INN and then the graph convolutional network and some hybrid models that combines multiple deep learning models. And the common idea of those different kinds of the models is to imitate the propagation of both spatial and temporal correlations from the traffic data, such that the periodical pattern and also the upstream and downstream patterns from the traffic data can be captured to infer the predicting results. This is all about the traffic prediction. And actually, this is also the last topic that I'd like to share with you today. So I have talked about the map generation from trajectory data, destination prediction from sub-trajectories, and travel time estimation and traffic prediction. In fact, there are still some other applications that apply AI techniques and in particular the deep learning techniques to deal with the spatial temporal data. For example, like the travel mode detection, which aims to detect the traveling mode from the user's moving trajectories and to see whether the user are taking bus or driving or walking. And also the trajectory user linking that tries to match the trajectory data for different users. Or given the trajectory data for one specific person, it tries to learn from data itself that whose trajectories they are. And we also have the taxi demand forecasting, route recommendation, and traffic light control, and so on and so forth. So what do you think are the advantages and disadvantages for applying deep learning techniques to deal with the spatial temporal data and address the corresponding problems in different application domains? I have summarized a few pros and cons for this kind of techniques. As for the pros, the deep learning based solutions can actually learn and capture the non-linear correlations from the spatial temporal data and specifically the spatial temporal dependence from the data. And these kind of models are completely data-driven models. We don't need to have too much prior knowledge about the data set or the rationale of the problem. So it requires less human interfere. Like we know we don't need to tell we don't need to tell the model step by step for how to get the output. Although we still need to design our model and train and also tune the parameters. And usually, the deep learning based models can get better performance compared with the traditional method and can address some complicated problems that are very difficult to address by developing a deterministic algorithm. In terms of the disadvantage, a very common and very hard to avoid problem is the interpretability. We usually cannot understand how and why this model works, and we don't understand what is the meaning of different parameters in the model. And the other issue is that this kind of models usually require a large amount of data for training. Otherwise, the performance should be very undesirable. And it also requires very high computational costs for model training and also the data pre-processing. And the last and the most important thing is that this kind of models cannot handle some problems that require 100% accuracy. At least so far, it is very difficult to achieve one zero error model. Yeah, to my understanding. So if you know some kind of model that can achieve zero error and can do the deterministic algorithms, so please let me know. However, this is still an ongoing and developing technology, and it is also improving very fast day by day, right? So hopefully, more and more techniques can be proposed to provide convenience to our life and also to make contribution for the development of our society. And maybe you're also one of the contributors. Okay, this is all about today's lecture. All the contents will not be included in your final exam. But if you have any question, feel free to email me and feel free to have discussions. Thank you.